Okay, page 16.
Yeah, we did.
It's not scratching out. Bro, what a trash world. So we've covered notes for 9.1 and 9.2. Your quiz is tomorrow, covering units 6 through 8. So I encourage you guys to review through worksheets 1 and 2. Tomorrow, I will do a help session. I'll probably move it up to 7:15, where I'll go through worksheet 3 and I'll answer any questions that you guys have. So you'll see one of each of the topics that we've covered from our previous unit. All right. You get to use your calculator. But you'll need to show all your steps. Any questions about the quiz for tomorrow? So today we'll cover 9.3. I know there's kind of like a backlog of homework, so I'm going to kind of split them up over the course of next week. So probably on Monday, I'll check your worksheets 1 and 2 from the quiz review, and then also 9.1 and 9.2 homework. And then what we do 9.3, I'll probably check that on Tuesday and just allow for us to kind of catch up with our homework. Okay, so I want us to recall arc length formula from our previous unit. We can adapt this arc length for parametric equations. So if an equation has an x equation, if there's an x equation in terms of t and there's a y equation in terms of t, we can adapt it into something that can work for us to find arc length. So we can recall a couple of things here. We know that f prime can be rewritten it's basically, or dy dx, right? This f prime is really dy dx. We can rewrite that dy dx as dy dt over dx dt. And then we're squaring it, right? We're just looking at what's inside, trying to adapt what's coming out of this here. And if we want to add these two together, we can kind of think of it as setting up common denominators, right? So isn't this the same thing as saying dx over dt over dx over dt squared plus dy over dt? Right, we're just taking what's inside the radical and just kind of creating our parametric forms into this. Now, we don't have to worry about the proof in terms of after this, as long as we can get to, as long as we know what the arc length and parametric form is, but I just want to show you that these are very much connected. Now, this is dx over dt in the denominator is really dt over dx in the numerator. And that will allow us to isolate this dx over dt squared plus dy over dt squared. So then our arc length is really adapting this and putting a square root over everything. The dx squared under the square root basically will cancel out with this dx over here. And then the dt squared under the square root, which is can be pulled out as dt. So really, this is what we have. Just wanted to show that these are the same. It's just that this is in rectangular form and this is in parametric form. I just want to say that over the next few sections, everything will just feel kind of intuitive. Like you already kind of know how to do all this. It's either finding integral of this or derivative of that. It's just in a different form, but nothing really feels new. At least not until polar. When we get to polar, then things will feel like things will feel like we need to we need to slow down when we get to polar. But with this, I think a lot of it is, like even if I didn't teach you this, you could probably figure it out just by using your previous knowledge. Okay, so number one here, for each set of parametric equation, find the length of the curve on the given interval. X of t equals cosine of t, y of t equals sine of t. So really, I can just find x prime and y prime, right? X prime and y prime will represent my dx dt and dy dt, and just have to kind of put it into my form here. So let's find x prime. Cosine is just negative sine of t. Y prime, sine is just cosine of t. Put it into my arc length formula, integral from 0 to 2 pi. Dx dt squared, so that's negative sine of t squared. Dy dt, that's my y prime, cosine t squared. What do you know about sine squared plus cosine squared? It's 1. So really, I'm just left with integral of square root of 1, which is just 1. Power rule, 1 becomes what? T. Okay, try number 2. Should feel pretty straightforward as well. Find your x prime, find your y prime. X prime is -4, y prime is 7. Square root of x prime squared plus y prime squared ends up giving us root 65. Root 65 is just a constant. The constant's antiderivative is just a linear root 65t. Plug in my upper and lower bounds. My arc length is 2 root 65. Any questions? All right, page 17. Let's try example 1. Any questions with number 1? Number 2, same idea. Just keep in mind that your a over 2 and your b over 2 is just some coefficient. It's not a variable. It's just some number that's hanging out in front of t. And when you find your arc length, your a and b will remain in your answer. So see if you can try number 2. My derivative of x prime is just 2 times a over 2t, which is just at. Y prime is just 2 times b over 2 times t, which is just b times t. And if I clean this up, I can square a squared t squared plus b squared t squared. I can factor out that b squared, and I can pull that t completely out from under the radical. And if I do that, I get something that will feel a lot easier to work with, especially if we understand that the square root of a squared plus b squared is just some coefficient in front of t, right? So imagine we've got a squared plus b squared. We can do this because these are just a numeric value from 0 to 1 e dt. So really it's just the integral of t that you got to worry about, because there's just some number that we're able to just push out in front, right? We can't do this if this is a variable, but we can do this if these are just a numeric constant. So now the only thing we got to worry about calculus-wise is power rule for t, p squared over 2, plug in upper and lower bound, the coefficient which is hanging out in front of my solution. Okay, number 3. Number 3 requires a bit more calculus procedure with use substitution. Any questions with 3? Yeah, we did have to kind of GCF manipulate it into a form where we can more easily go to use substitution, identify the u value, seeing that it's going to work out. Right, number 4. Yeah, we should be able to rely on our trig identity to help us out with number 4. Sine squared plus cosine squared equals 1. I think 5 is pretty straightforward as well. Right here. It ended up getting removed because the -5 times -5 is positive, so we just dropped that negative. All right, page 18. This shouldn't take very long for page 18. So after this, I would like for us to look at some of the AP problems from 9.2, since it has some of the arc length in it on AP practice. So after page 18, after we go through page 18, we'll go to page 13 and 14 and finish up there. Yeah. Or bottom shelf, the unit 9 apple. So for each of these problems, you're just finding x prime and y prime and putting into your arc length formula, right? Okay, we're done with page 18. Let's see if we can go to page 13. Let's look at some of those. All right, page 14. Let's do page 14 and 15 after 18. Do some of those arc length problems in AP form. Finish with page 14 and 15. Again, page 14 and 15. I'll switch over to that page in a little bit. Number 5 is pretty straightforward. Number 6, you do need to factor and take out that GCF completely outside of the square root to allow for us to go through U substitution. Okay, let's do one more problem on page 15. We need to find x prime. We need to find y prime, but y prime requires chain rule. So cosine parentheses c squared becomes 2 cosine of t minus negative sine of t. We really need to use identity, double angle identity, to get it into something that is helpful for us. So 2 cosine times negative sine, the same thing as sine of 2t, because it has that form, and that allows us to better fit into what we need with u substitution with our argument. Once we get that accounted for, then it becomes a lot more straightforward. Put it into your argument formula. Everything's in terms of sine. Things clean up to just to be root 5 sine of 2t. The square root can go away. The square root and the square can cancel each other out. And really the only thing we got to worry about is that 2t with u substitution before we plug in our upper and lower bounds. Yep.
Why is it the square root of 5?
Sorry, square root of what?
Like why is it the answer?
Oh. Oh, so I think there's a negative that carries over. here. So positive, positive, positive. Which part are we getting negatives?
Oh, no.
Yeah, I did carry this negative through. That negative should stay before I evaluate my bounds. Okay, we pretty much completed all of 9.3. The only thing that remains for us to catch up is to finish off 9.1 and 9.2 AP and class work problems in our packet, but I'll check that on Monday. So I think on Monday I'll check 9.1, 9.2, and your quiz review worksheets 1 and 2. But tonight you can just focus on studying for your quiz tomorrow. I would encourage you guys to look through worksheets 1 and 2. And then use worksheet 3 as your kind of mock quiz tonight. See how comfortable you are with all the topics. And then tomorrow morning, 7:15, I'll work through each of the problems in worksheet 3, as well as any questions that you guys may have. Okay. Also, one more thing is that next week, Monday and Tuesday, we're going to do vector value functions, which I think you'll find it pretty straightforward because you're just using first semester knowledge and everything will just feel, I think, pretty straightforward. When we get to polar graphs on Wednesday, we'll really need to slow down. That's where, I think we're going to need more time to kind of let that sink in. So starting next Wednesday, we'll really slow down with polar and spend time with that. But yeah, I'll send out a reminder this afternoon. And then over the weekend, I'll also send out a reminder about what homework I'm going to be checking next Monday. All right, come get your phones.
I know I'm missing some stuff from the first or second week. So do you know what those are so I can make them up?
Yeah, go ahead.
Even so, be like 5 minutes. Because I can find my lines.
6.12 and 7.4.
7.4.
Yeah.
Okay.
Did you see that?
I got told like 2 days ago.
I got told Mexico's gonna still that I think. Like I know like what we're saying and where we're going, but like our